Sweet. Thank you. All right, let's get started. The next tutorial is going to be run by Andy again. We'll start by moving over to the CryoCloud book back to the external directory there. And we're gonna this time pick the ICESat-2 ATL10 H5coro tutorial. And I'll turn it over to Andy.
Right, great.
This thing.
I can, yeah. Okay, so we, NSIDC have been kind of doing these tutorials both for NSIDC and also for the NASA OpenScapes group for some time. We got to the point where we're like, we are demonstrating what is generally toy examples, right? We want you to learn, we want you to kind of have small snippets that are hopefully easy to understand and implement for you. But we've been realizing that really, if we're going to demonstrate the power of cloud, then we need to scale up and start doing something kind of workflows that you will be doing in your everyday work life. I'm not sure that this necessarily goes all the way there, but this is the bare bones that should allow you to scale up. So what I'm going to be showing you is essentially trying to recreate the ATL20 gridded sea ice freeboard product. And that uses information from ATL10, which is the along track freeboards. I'm just going to focus on the Ross Sea region for the time being, but you can scale it up to Antarctica. We're just doing it for a single month, September 2020. At the NSIDC DAC user working group last week, Alec Petty ran this for 3 years worth of data, and it took a really short time to run. So this hopefully has the ability for you to scale up and use it, whether you're using it to try and regrid ATL06 or whatever other data set you want to work with if sea ice is not float your boat. So I'm gonna run through this. I'm not going to be live coding because there's a lot of stuff in here that I just will take me ages to type, and you don't want to see me make that many typos. So the first thing to do is we need to install some versions of libraries that are not in the CryoCloud environment yet. And we're going to be using that pip install approach that you saw Wilson use just a moment ago, and Tasha spoke about. I've been using the old style of using an explanation point to do pip, but I'm going to change these in here so that they use the pip magic. We're going to be using a new version of Earth Access, which allows us to take advantage of some of the new features that have been implemented in a package called H5coro. Now, you've probably heard a lot about slide rule this week. H5coro is a cloud reader for one-dimensional HDF5 files in the cloud, and it was developed by JP Swinsky and the slide rule team, which Tyler and Ben are part, to allow performant access of cloud-hosted data. And we've done some testing with H5coro. We did it at the ICESat-2 Hack Week. and it is just way faster than using standard HDF5 readers. So we're going to be using H5coro as well, and we had to make some changes to Earth Access to make that work. So I'm also using this capture magic command at the top here. I know this install works. But what it does is to create a whole stream of output as it's installing these libraries. So capture just captures all that output and prevents it from appearing on the screen. I also want to draw your attention to kind of, well, I guess three things, but two things in particular. One, we want to first of all uninstall Earth Access in H5coro because we want to put new versions in and we don't want the old versions hanging around. But I want to be very specific about, and I'll highlight this because those of you online can't see what I'm pointing to on the screen very well. So I want to be very specific about the version of Earth Access. So pip and conda allow us to specify the version. We're using version 6.1. And then here at the bottom, you'll see that this is a little different. This is a little different. We're actually, this version of H5coro is under development. We know it works, but it's not yet in the PyPy, which is the Python package manager. So we're going to install that code directly from the GitHub repo. Everything's there, so it works nicely as a package. It's just not available by the normal routes, so we have to go to GitHub. So these are two kind of key things to remember, especially as you're kind of getting towards using cutting edge kind of versions of tools, that you can install stuff from your own repos or other people's repos to get them working as packages on the machine. So, and then we're going to install a bunch of other packages. The import for OS and setting this use PyGeos equals 0 is to force GeoPandas to use Shapely instead of a package called PyGeos. Otherwise, it throws a warning, and I got tired of seeing the warning, and it tells me to do this if I don't want to see it, so I just followed along. We're going to use Earth Access. I'm going to be using NumPy. I'm going to be using a few features from Pandas, this utility called datetime, and then I'm going to be doing some resampling to a grid, and affine and affine matrices are really useful for doing that kind of resampling work. So I'm going to be using this affine object from that library, and then usual suspects, matplotlib and cartopy for doing the plotting. And then we've written some helper functions from that we originally put in a directory called H5Cloud in this module called read ATL10. In actual fact, if you look in your directory structure here, you'll see that read ATL10 actually is sitting in the current directory. So I'm going to ask you, before we do this install, well, I'll run it and show you how it fails first, and then we will correct it. So it's telling me that it can't find a module named H5Cloud. And I realized, as I said, read ATL10 is actually in our directory structure. So I just need to, in this case, change the path to just look directly for read ATL10 rather than this directory called H5Cloud. So if you want to go ahead and just delete that H5Cloud from that line, it should work. And it's telling us that the version of Earth Access that we're using is 6.1. Then we're going to do this authentication step next. And I'm going to, if you need to type your credentials in again, go ahead and do that. I'll just wait for a while, for a moment while you do that. You should be pretty good. Everybody got lucky with typing their credentials in. So and this is kind of just setting a few parameters. I want to look at the Ross Sea region. I have put in a bounding box for Antarctica as well, but all this section is saying is, if this region or the region argument is Antarctica, use this bounding box. Otherwise, use the Ross Sea bounding box. I want to restrict it to Ross Sea. And then I'm setting the year that we begin and the year end. They're the same because we're just looking at September of that year. So I'll set those. And then this is the search part. And we're doing there's a lot going on here because we wanted to allow it to be expanded to multiple years. So we do a granular search for each year. I set the dates that I want to search for, and I'm formatting them as a string, so it comes out in year, month, day format. And then we do that search for 1 year. The results get fed into a Python dictionary that we're calling ATL10 here, that is indexed by that year. And it goes through however many years you decide you want to run it for. And then we're going to print out some information about how much data we've actually pulled as a result of that. It's just going to run through once because we're only using 1 year. And it finds 59 granules. Just going to shrink this down a little bit so that I can see what's going on. Oop. There we go. So it's still running because it's even though we're getting results printed out, it takes a while. So that's 5 gig of data almost that we've downloaded there, 59 granules that cover that Ross Sea region. And then we want to read this data in. Right, and this I'm using this helper function read ATL10, but we're also got a couple of other helper functions here. We've got get data links, which all that does is to just change the links so that they point to the S3 bucket where the data is stored, because we're still working in the cloud. That little setting up of credentials that Wilson just showed, I've encapsulated that in a function just to make it a little easier. And then we use this function read ATL10, and I just want to show you a little bit about how this works, because it's important that ICESat-2 files, each product has a different file structure, and we want to get different data from different places. So sometimes you have to write kind of like bespoke functions to get the data. And because we're using H5coro to do this, we've had to do a few little changes here to make it work. So there are actually 2 functions nested inside of each other. And the reason we do that is so that we can parallelize the whole process. So read ATL10 takes in files. If we needed bounding box information, if we wanted to constrain that data down even more, we could do that. There's an executors variable that sets the number of threads we can use. So each processor can spin off processes in different threads, and that's how we parallelize it. We're using, we're only going to work on a single processor, but we can still have a number of threads working. We can set it if we want to work locally. We're going to be working in the cloud, and we feed in the credentials. So we set up the environment first, whether it's local or in the cloud, and we have to use different drivers. That's what this section here, this if environment section does. We then need to, because we need to convert the delta time variable, we set the GPS epoch, which is 6th of January 1980. That's when the GPS system started, or when the time stamp for that starts. And then what we're doing in this H5coro reader, just shrink it down a little bit. So we initialize H5coro. That's essentially a file object, and we're running this on each file, but we're running the files on separate threads. So we open a file object, we get some ancillary data sets. We need to know the orientation, because we're only using strong beams, and that is dependent on which way the ICESat-2 satellite is oriented. So we get that information from the file, and we need to get some more information about how many seconds to add to the delta time for the data in the file. So we grab that information that's held in the Atlas SDP GPS epoch. Wilson also talked about data dictionaries. So if you can find all this information in data dictionaries. And then H5coro reads the data sets. And what this is doing is actually searching through the HDF5 file, looking at the file level metadata and where the bytes for these particular variables are held. And then we set up, we say, okay, we want these particular data sets. We want latitude, we want longitude, because we need to know where they are. We want to get delta time, because that's a useful coordinate to have. And in order to do this gridding, we need to know the segment length and the freeboard heights. And I've also said, well, I want to know segment distance, and I want to know the type of the segment, because maybe I want to do something with whether it's ice, whether it's a lead, or whether it's a specular lead. So I've left that data in there, but you can set up a number of data sets that you want to read just by feeding in these paths. And then we go through the process of finding where that data is within the file. And then we just loop through, because we want to use all the strong beams, we loop through reading that data and creating the data set. And what I do is I read it into a GeoPandas data frame, just as Wilson showed for some of the other data here. And I know we use X-ray a lot for reading data. I'm coming to the conclusion that oftentimes reading stuff into a GeoPandas data frame, just because it's in a long track data, allows you to do a little more, or some tasks a lot more efficiently. It's my preference, but it's worth checking out. And then we return all of that we concatenate all that information together and return it as a single big pandas data frame. And now I have to find the notebook that I was working in. There we go. Great. So let's run this. So this is opening up the file object. It's getting information about where the data is in each file, and it's stuffing it into a GeoPandas data frame. And this is 59 files. It's 5 gigabytes of data. And we're using this library called PDQM, which allows this multi-threading. So we're actually doing this in parallel in the cloud. And the progress bars tell you how much time you've got to go to get coffee or answer email or whatever. So you can see how far along, but you can see it's actually going through pretty fast, right? I have tried this for the whole of Antarctica. It does take obviously a little longer, but it's still pretty fast. And I'm timing it. I'm using the time magic command to get that. So we're halfway through. Any questions? Any questions online?
Not yet.
They've obviously realized they've got 30% of however long it's going to take to go get coffee. Okay. So
It says it's one of the coolest things about H5coro. We can actually use threading and speed things up.
that's Louise.
Yeah.
Yes. Yeah. Okay. So 5 gig of data took 1.5 minutes. run through and generate a data frame. And I think what I didn't point out was I was doing that, creating the geometry column for the GeoPandas data frame as I'm going through each of those files. So this is our data frame, right? And I like to think of GeoPandas as you can basically do anything you would do in a GIS, but you're not having to pay a license fee to Esri. So I like that. You have to make your own maps. You don't have all the cool features that they add, but it's essentially a GIS at the command line. So now we're going to go into gridding that data. So we've got all this data. We've got the points in latitude and longitude. They are in the WGS-84 coordinate reference system. And Wilson was talking about that. I actually put some links in the Zoom chat for some resources that were put together by David Sheen during the ICESat-2 Hack Week about coordinate reference systems. And there's also a really great notebook that Tyler and several other people put together for one of the previous Hack Weeks that kind of really go into this in detail. And the reason I want to draw your attention to this is I'm setting this to WGS-84. That's a two-dimensional coordinate reference system, right? And it's the coordinate reference system that the GPS system uses. But to be truly effective, we should be using ICESat-2 data with a 3D coordinate reference system, which is tied to a reference frame, which is, the plates on the Earth are moving. And so where you are in relationship to those plates is also changing. And so we have to update our coordinate reference systems and realize them frequently in order to make sure that we are where we are on the Earth. And it gets really complicated, as David Sheen points out in his help document, but we really need to be using, and I think it's 7139 is the EPSG code. At the moment, I'm using 4326, which is WGS-84, but we need to be aware of that. And I'm going to update this once I can get some more information in there. So we're gonna move on to gridding that track data. And so here, I want to put the ATL20 data set is in the polar stereographic grid. What I want to show is that we don't have to, if we're working in the cloud and we have this computing power and we want to do our own gridding and stuff, we don't have to work in polar stereographic, right? We can work in the EaseGrid version 2, and in this case we're in the southern hemisphere, so south, or we can choose an Albers equal area projection and some other coordinate reference system, and we can choose the grid resolution that we want to work in. Most of our data is going into a 25-kilometer grid. I think it's a reasonable thing to do given the amount of data we have and being able to get enough data into grid cells. But I just want to say we can choose a 6 1/4 if we want, right? 6 1/4 kilometer grid. So that's what I'm doing here. I'm saying, right, let's set the coordinate reference system for the grid we want to use to be EaseGrid 2 south, and the EPSG code for that is 6932. And then I'm setting up the parameters for the grid that we want to use, and I'm just focusing a small grid over the Ross Sea region. There's an appendix to this notebook that shows you how I came up with the number of rows, number of columns, the width, and the upper left X and Y coordinates for that grid. But the reason I'm showing this here is that I want to make the point that the coordinate reference system is distinct from the grid we choose. I could create my own grid. There's an infinite number of grids that I can create for a particular coordinate reference system. In this case, I'm just creating my own that sits over the Ross Sea. And in order to do that, I need to know the shape of that grid, the dimensions, that's the number of row and columns, I need to know the resolution of the grid. I'm assuming that column width or pixel width and height are the same, 10 kilometers. And I want to, and I need to define the upper left X and Y of that grid. And then here I'm just defining a map extent so that when I come to plot it, I don't have to type all that information in. I'm using these grid parameters to do that. Any questions on coordinate reference systems? Okay, so what I need to do in order to start the resampling is to go from the WGS-84 two-dimensional coordinate reference system to the ICESat-2 South coordinate reference system. And GeoPandas has this 2CRS tool to allow us to do that reprojection. And so this takes a little while because it's actually got to go through like something like 15 million rows of data, but it does actually end up doing it pretty fast. And I'll use that time to talk a little bit. Oh, there you go, 16 seconds, didn't talk fast enough. But we're just going to use a drop in the bucket resampling scheme, right? So if a segment or the center point of a segment falls within a grid cell, I'm going to say it belongs to that particular grid cell. And then I'm going to create statistics for all the segments that fall within that particular grid cell. In order to work this out, there are some tools out there to do it. PyResample will do it, but this is it's actually a simple thing to do, and it's worth demonstrating. So this is just saying that in projected coordinates in that ICESat-2 South coordinate system, there is a relationship between the column and the row position within your grid, described by these two equations here, right? X and Y are related to column and row with using those parameters of width, height, and the upper left corner of the upper left pixel. We can express that in matrix form, and this is the affine transformation, right? Or a reduced affine transformation. So it relates. So with this, what this matrix equation is saying, linear algebra equation is saying, is exactly the same thing as this equation up here. And we can encode that within this affine transformation using the affine class of the affine package. And all I need to feed in is the width, the upper left X, the height, and the upper left Y. At the moment, it doesn't know about the shape of the grid. We're just saying, I want to relate every point in projected coordinates to a column and row. And what we get out of that is a column and row expressed as a real number, because the spatial coordinate system of the grid is continuous, right? It's all real numbers. So imagine kind of having a map and laying a piece of gridded piece of paper over it and identifying where those points are, and the origin of that grid is in the upper left corner. Then you can count across the number of columns and rows where a particular point is, and that's what you're getting out of doing this affine transformation. So what I'm doing here is exactly that operation. I'm finding the coordinates in grid space of each point that we have in that GeoPandas data frame. And then I'm calculating a single unique number, the array index. Imagine I've unfolded that grid, so it's now a vector, and each cell in that vector has a unique index. And I'm just calculating what that unique index is for that vector so I can put points into it. And I'm using the geometry information in the GeoPandas data frame, and we got an error. Oh, all right. And this is one of the problems with using notebooks, is that you need to make sure that your cells are run in order. And if you have a little thin cell, it becomes an orphan. and you need to repatriate it. So we're timing this. Doesn't take too long. I think it takes like a minute or so to do. But now we know which grid cells each of those segments falls in. Any questions? There's beer in the fridge. Anyone want to do a dance, tell a joke? Are there any questions online? So as I say, I'm using a drop in the bucket approach. And I've spoken with Alec, Alec Petty, who developed the ATL-20, and there's lots of other interpolation schemes. We could get pretty clever with how we do it. It's just this is the simplest and maybe kind of, we're not making any assumptions, but we could use bilinear interpolation. We could use some Gaussian basis function in order to do this. If we want to code it up, we'd have to change bits of this code, but the notebook allows you to play around with those things. And one of the things I was thinking of as we were talking about slide rule and seeing some of the things that people are doing, slide rule, people are working with the slide rule team to get their own processing streams into the cloud. But there's a step before that in that you need to really do some development work and figure things out. And this kind of notebook and this kind of workflow allows you to start doing some of that development work before you call up Tyler and JP and say, hey, can you do this for me? So now in my grid index, I've said that if any point falls outside of the extent of the grid, I'm going to code it as -1. And you can see here on the left, on the right here, let's get rid of this. You can see here that we've got a bunch of -1s for grid index. What I'm doing here in this step is to just get rid of those -1s. Then we calculate some cell mean statistics within ATL-20. They look at the mean segment length that fall within each grid cell. They calculate a mean freeboard weighted by segment length. So we're not biasing kind of lots of short segments and ignoring some of the longer segments. And then we create a standard deviation also weighted by segment length. And I just code those up into this into these functions here. I'm still working with the GeoPandas data frame. And I want to use an apply method, which is part of GeoPandas. If you're familiar with pandas and GeoPandas, it essentially just applies a function to every row within the data frame. And so I wrap all these functions into a function that I imaginatively call allfuncs. And you can take a look at this, but testing your functions is a good idea. So these cells actually prove that what I did is doing what I think I did. So I have a test data frame that I've put the grid index, I've put the segment length, I've put some beam height information in. I've calculated what the expected values are for that in another data frame. I run the test run that test data frame on allfuncs to get a result. And then this PD testing assert frame equal is just saying, are my results, do they match what I expect? And I don't want to worry about using this assert frame equal means that I don't have to worry about a lot of decimal places, right? I can get it almost right. And that passes. If it didn't pass, it would raise an error. And then let's run it on all the data. So now we've got everything with unique IDs. we're calculating grid cell statistics for all the segments that fall within a particular pixel, and that's what this group by grid index argument is doing. So now what we've got to do is to take this list of grid cell statistics indexed by a unique identifier that relates to the grid cell they fall in, and just put all those values into a grid. And that's what this series to grid is doing. You can take a look at the function just to see exactly what I'm doing there. We'll run it, takes 4 seconds. And just to make sure that we're getting something that's sensible, let's just plot the image. I'm using ImShow here. And this is just a plot of the number of segments that actually went into each of those, each grid cell. But this is a representation, a raster of those grid cell statistics. Let's do something a little fancier here and plot that data. And when you're using maps, it needs to download some vector data, so it gives you a little warning. And those are the segment counts for each for all that data. So for the Ross Sea region, and this area here is ice shelf. So it's not included in the sea ice data set, but these are all sea ice values. Now we're probably more interested in the freeboard. So let's plot mean freeboard, and also let's make it a little more useful by adding a color bar to it with a label. Oh yeah, that's amazing. Normally I would just try and stuff a U in there and get a similar error, but there you go. So let's go with that. And now we're seeing mean freeboard height. So that's essentially a workflow that you can use for trying to improve on some of the gridded data sets that are out there in the cloud. You're never having to download data to your local machine. Everything's done in memory, and we're able to parallelize the whole process. So hopefully it's a lot quicker than you would normally have. And there's many improvements that we could make to this, or you could make to this, using Dask and other libraries, and writing some of the code in a little more intelligent way than I've done it. So that's it. That's all I have. So thank you very much for your attention.
So I had a question on this. Andy, how long would this normally take without the cloud?
Well, downloading 5 gig of data, yeah. I mean, I think the largest time sink for this is just downloading data to your machine. And I was going to try that and give you a time, but I don't have that information. But I think, when I just, and you can try this yourself, if you just do a run all on all these cells, it's going to rip through pretty quickly. Like each of those steps were all kind of roughly, certainly less than 2 minutes each step where you had a lot of work. So the reading, the processing and everything, takes less than 10 minutes, maybe less than 5. So I think that's way shorter than trying to download all that data. And also having to worry about where do you store it and stuff. And you can share that around. Like, I can send it to Alec, or I can send it to Tyler and say, hey, let's build on it. Well, what do you think? What stupid things have I done?
An H5coro is so much faster than you S3 file or whatever.
Yeah.
Yeah. H5coro, yeah. H5, the one caveat with H5coro is that it only reads one-dimensional data at the moment. But
It should only be able to read ICESat-2 data
yes, yeah,
specifically, right?
uh-huh.
It's not any,
But the one-dimensionality.
okay.
Yeah, I will say we've done some testing. If you want to, I get a presentation at the end so I can see Daphne's working group on benchmarking some different reading approaches. We had a project at the ICESat-2 Hack Week where we did that benchmarking work. One of the things we found is using a package called the chunk, which kind of builds a lookup table for where the data is in the file. That actually, if you use that with X-ray, then that's a really performant way of reading data, almost as fast as using H5coro. And it's a lot more extensive generalized because you can read SDFRs, you can read multi-dimensional data. So that's also a good thing to check out. So what we're doing is this is the quickest way we think to read the track data,
Yeah.
the low level ICESat-2 products, but if you want to do other things,
So what Andy said was that the online group may not have heard was that CryoCloud is another way of reading in this data that is almost as performative as H5coro, but can be generalized to other kinds of data sets. So you can check out H5coro to do fast read-ins, because just using H5Pi for this would be a lot slower to read in each data set segment. Any other questions or comments on this tutorial? Oh yeah. So Luis says, this is one of the coolest things about H5coro. We can actually use threading and speed things up. We can also parallelize if even further with Dask. So those are ways that you can speed this up to make it even faster than 5 minutes to run all of this data.
Dask, you could have all of the operations kind of just build a set of things for it to do, and then it will thread it out and do all of this. It wouldn't be able to do the like really quite about. And then once you have all this stuff in memory, you could mess around with pixel size or your projection, because you have all the long-term data in there read, so you could do the testing you want to do the grid as well.
Yeah, so Tyler said that once you have it all read in, then you can play with it pretty easily from there without having to do anything substantial otherwise.
Yeah, so please use it and please break it and please talk about it.
The example from the using the chunk that made available somewhere.
Yeah, if you look on the ICESat-2 GitHub, it's there. I'll send you the link as well.
So it's probably in here. What tutorial was it?
Oh, it's not a tutorial, it's a project.
Oh, okay.
And I was searching around, I couldn't find a quick way to get this project.
Yeah, it looks like it's not listed here. We'd have to go to the GitHub.
I have it up. So I'll post this down.
Yeah, it'll be in here in their GitHub repo. All right, so we have some remaining time. I want to be cognizant of the fact that people might be flying out. I also have to have a flight. The things that we can do right now is you can ask general questions about, tools and what's coming onto CryoCloud. I could walk you through, basically we went through data access using IcePix and Earth Access. There's also stat catalogs that I have short tutorials for. If you want to access something like I have examples of accessing Landsat data and Sentinel-2 data. We can walk through those really quickly, or we can open up your code and you can try to add some of this data access into your code and run it on CryoCloud. So in that order, anything people are excited about, just type up and we can go through that. Does anyone want to go through data access code?
I would like to do the same stuff, but I think it's
Okay.
can we use the same code and just change the product? You might.
Yeah, I mean, I think you could use the read ATL as a template, and then but we have to figure out what data sets you want to read.
Yeah, so when you go to change it, it's basically yeah, where is it? Read ATL. So like these names right here would be different when you, and these right here would all be different in the different data products, but generally this would work once you adjust for those.
And I would say that that's one of the very key things about ICESat is that it has a lot of the, actually I think pretty much it will do for every product, ICESat-2 product, it will generate a list of variables and you have to start picking those variables from that. So that's a very huge advantage.
So what Andy said is that you can use IcePix to, it'll produce a list of variables for every product. So you can flip through those and choose which ones you want and select only those using IcePix. So that's a nice thing about it.
And if you go to the tutorials in the ICESat, this year's ICESat-2 Hack Week, I have a nice fix tutorial in there that I think explains how to do that. Thank you.
Yeah, I have some information about it. But AG, you're gonna do a session.
Yeah.
And you're gonna have also Zoom.
Yeah, it'll be on Zoom. I'm still waiting to hear what the logistics of it are. I don't know anything about, I hope they don't charge people. At least I'm gonna, I'll do it on Zoom. Yeah, I'll make sure it's on Zoom. And some of this will be the same. There will be a CryoCloud demo at the beginning so people can learn how to use that. But then we'll get into more of the using Dask, using parallelization. That'll be run by Ellie Abrams. Johnny Kingslake's going to go through AP Res data and how to process that and create cloud optimized data sets and kind of the thought process of how to optimize those data formats. GRIMP is going to be demonstrated by Ian Joggin. Sophie is going to go through GHub and I believe, and then, yeah, we're going to do some like visualization and whatnot. It's kind of similar to the ICESat-2 tutorial we went through, but a different one. And then I'll probably talk a bit about how to open science your publications. So like how to make everything more transparent, reproducible, reusable. Cool. Does anyone want to go? Yeah, go ahead, Ben.
You said you guys went through a lot of things, right? Actually, and you talked about some data and access to NSIC. I'm interested in your perspective on how to optimize other data sets that I was mentioning already that are posted on the CRYSIS server, but usually they're stored as like a meta file. And not that I'm gonna like think on this project, but like if you would envision a path or how it would be easiest to move that, what would be your strategy in terms of how to optimize that for cloud?
Some of that, so like there is the option of like actually changing the data format and creating a new copy in a new data format that would make it faster. Tyler or someone can correct me if I'm wrong, but generally you can still like read that data in
Yeah.
and stream it depending on the source sometimes, and you won't actually have to download it. You just use the URLs to open it. It's just much slower. Not much slower, but like, I mean, it's much faster than still downloading the data, but that is another option.
Yeah, and with cloud. One-dimensional, two-dimensional, the actual format, that's where it might change. It also depends on, do you want rich metadata, or can you work with a slim file? There's a file type for a long track or just one deep Parquet or Parquet. Those are extraordinarily fast. You can load in data sets that are really seconds. But then when you get into reuse the data set, they kind of saw that I typically use, and if it's just pure 2D, the COGS, the unoptimized speed, that's great. But with Parquet and COGS, you don't have the rich metadata, so it's sort of what you want. You can create, like what Taco said, a stack catalog that can have all that metadata that can drive your COGS. But yeah, but it depends, I guess, on what you want.
Parquet,
Yeah. There's also a repository put together by the Pangea group, Pangea 4. What they do, as long as your data, the data that you want to work with, is accessible somewhere on the web, then you can basically write a recipe to take that data and to convert it to a cloud optimized format. And they will then review that recipe and figure out, maybe make some changes, or ask you to make some changes, get it working so it's performant. And then they will post that data, run that recipe and post that data in the cloud. So that I don't know. Do you know part of it? I mean, my understanding is it is for free. It's funded by NASA or the NSF, so it's free at the moment.
Do you mind if I email you about that? You send it through Pangeo?
Pangeo Forge.
Yeah.
I
I don't know breakdown. I haven't used it myself, but they are super helpful, super excited to use it.
Yeah.
So that might be worth looking at as well.
For the online people, we just discussed there's a few different kinds of formats, cloud optimized formats that can work for transitioning your code. And then there's Pangeo Forge, or sorry, not code, your data. Then there's also Pangeo Forge, where you can produce a recipe for converting your metadata into something that's more cloud optimized, and that allows that you can host that data in Pangeo Forge for free, and it'll convert it and make it cloud optimized. So yeah, Tyler and Andy are good people to talk to for that. The other thing I want to point you to, we have these tutorials. The ATL10 H5coro is in our Jupyter book, and also the ATL15 tutorial we just went through. There's a Landsat tutorial, and a tutorial that kind of goes more through X-ray and Pandas if you want to learn more about those. And then in our how-tos, we have data access and the Sentinel-2 Cloud Access, which is a stack catalog that's included in here to like ways that you can access stack catalog data. So that's any data set that has a stack catalog that often is not in NASA. You can access those. There's other things like how to use the AWS S3 bucket that we have, how to create your own, and how to access the Scratch bucket so you can use a lot more temporary storage. The Scratch bucket allows you to quickly read and write data in storage that I think keeps it for 7 days. yeah, so there's some of that documentation already on our book if you want to access that. I won't walk through it. Anyone who wants to walk through their data or try and read in some cloud data into your current notebooks, we're happy to do that now for a little bit. I think anybody, we can stick around for questions. If anyone has any other questions, we can answer that now. Otherwise, like, you guys can definitely go enjoy the evening, get to your flight, whatever you need to do. Cool. All right. Join Slack. We invite everyone to our Slack, so you can ask us questions there too. Oh, sure. Does anyone online have anything else? Oh.
You sent out an email invite to Slack, or
We just invited you to our Slack. No, I think you were invited a while ago.
yeah.
Thanks everyone for joining online.